Dear students, in the previous lecture, I have explained you about two important thermodynamic parameters, internal energy and enthalpy. Internal energy is the heat absorbed or evolved, or you can say the energy exchange at constant temperature and constant volume. Enthalpy or the heat content is the heat exchange or energy exchange at constant temperature and constant pressure. Internal energy and enthalpy both are state functions, that is, they depend upon the initial and the final state of the system and not on the path, and both are extensive properties. I have also explained you that to find the exact value of internal energy is not possible. In the same way, to find out the exact value of enthalpy is also not possible. Dear children, when we do the experiments in the lab, they are under constant pressure, that is, under atmospheric pressure which hardly changes. It is almost constant. For example, there is a gaseous system and there is evolution of heat. And if there is expansion, then work has to be done by the system. Then some part of the heat is utilized to expand. Then the heat evolved will be less. And if there is contraction, then the work is done on the system and heat generated will be more. For an exothermic process, change in enthalpy and change in internal energy are negative. For endothermic reaction, delta H or delta U is positive. To find out the change in enthalpy, we can calculate it as the sum total of enthalpies of the products minus sum total enthalpies of the reactants. The relationship between internal energy and enthalpy. It is defined as the sum of internal energy to the product of pressure and volume, that is, H is equals to U plus PV. Or we can also say delta H is equals to delta U plus P delta V. Delta V is the change in the volume and delta U is the change in internal energy. Delta H is change in enthalpy. From the ideal gas equation, we know that PV is equals to nRT. So, in the equation delta H is equals to delta U plus P delta V, we can also use delta nRT. Delta N G. G is the subscript. It is the difference in the number of the moles of the gaseous products and the gaseous reactants. Enthalpy change. In a chemical reaction, the reactants change into products, and the enthalpy change accompanying the reaction is known as enthalpy change or the enthalpy of reaction, which can be exothermic or endothermic depending upon the energy state of the reactants and the products. Standard enthalpy of reactions. The standard enthalpy of reaction is the enthalpy change for a reaction when all the participating substances are in their standard states. The standard states of a substance at a specified temperature is its pure form at 1 bar. For example, ethanol at 298 Kelvin or 25 degrees Celsius and at 1 bar is in liquid state. To find out the standard values, we take the standard conditions. Enthalpy changes during phase transformations. Phase transformations means a substance only changes its phase or state. For example, when ice melts, it changes from the solid state to the liquid state. The formula remains H2O, and the melting of ice takes place at constant temperature and constant pressure. That temperature is known as melting point. The enthalpy change that accompanies melting of 1 mole of a solid substance in standard state is called standard enthalpy of fusion or molar enthalpy of fusion. Delta fusion H with a symbol. That symbol, which is a superscript, denotes that the conditions are standard. H2O solid gives H2O liquid. This is a fusion. Standard enthalpy of vaporization. When the liquid water changes into vapor state, this is vaporization. Amount of heat required to vaporize 1 mole of a liquid at constant temperature and under standard pressure, that is 1 bar, is called its standard enthalpy of vaporization or molar enthalpy of vaporization. Delta vaporization, we are using the VAP H with the superscript that denotes the standard conditions. Standard enthalpy of sublimation. In sublimation, a solid directly changes into liquid state. For example, naphthalene sublimes, or the solid carbon dioxide, which is a dry ice, also sublimes. When 1 mole of a substance changes directly from the solid state to the vapor state, that is the enthalpy of sublimation. During phase transformations like solid state, the change of solid state into liquid state or liquid state into vapor state, the processes are endothermic and the value of delta H will be positive. But when the reverse of the process takes place, for example, liquid water freezes and convert into ice, the magnitude of the enthalpy remains the same, but only the sign changes. The sign changes from positive to negative. Similarly, when the vapors condense to form the liquid water, again the magnitude of the enthalpy remains same, only the sign reverse. Standard enthalpy of formation. The standard enthalpy change for the formation of 1 mole of a compound from its elements in their most stable states of aggregation, also known as the reference states, is called standard molar enthalpy of formation. Its symbol is delta FH with the sign of standard states. The F is in the subscript. The reference states of an element is its most stable state of aggregation at 25 degrees Celsius and 1 bar pressure. The standard state for hydrogen is the gaseous state. For oxygen, again it is the gaseous state at 25 degrees Celsius and 1 bar pressure. Out of the allotropic forms of the carbon, that is diamond, graphite, fullerenes and other forms, graphite is the standard state for carbon. Similarly, out of many allotropic forms of the sulfur, rhombic sulfur is the standard state. Standard enthalpy of formation in the standard state is taken as 0. Now, I am taking 2 examples. H2 in the gaseous state plus half O2 in the gaseous state gives 1 mole of water in the liquid state. We must mention the states because these are the reference and the standard states. H2 in the gaseous state plus Br2 in the liquid state gives 2 moles of HBr in the gaseous state. Let me explain you that the second equation is not an example of standard enthalpy of formation because here 2 moles of HBr are formed, whereas the standard enthalpy of formation says that it should be 1 mole of the product formed from its element in the standard state. Enthalpies for different types of reactions. Enthalpy of combustion. Enthalpy of combustion is defined as the enthalpy change per mole or per unit amount of a substance when it undergoes combustion in all the reactants and products being in their standard state at the specified temperature. methane, that is CH4, in the gaseous state undergoes combustion, that is 2 moles of oxygen in the gaseous state to give CO2 and 2 moles of water. The reaction is exothermic and delta H is negative. Enthalpy of atomization. It is the enthalpy change on breaking 1 mole of bonds completely to obtain atoms in the gas phase. In the case of the diatomic molecules, the enthalpy of atomization is equals to the bond dissociation enthalpy. For example, hydrogen molecule. There is a covalent bond, a single covalent bond between the two hydrogen atoms. When we break 1 mole of hydrogen molecules into gaseous atoms, then the energy required to break these 1 moles of the covalent bond in the gaseous state is known as the enthalpy of atomization. In the case of hydrogen-like molecules like chlorine, etc., that is the diatomic molecules, the enthalpy of atomization is equals to the bond dissociation enthalpy. But in the case of the polyatomic molecules, the bond dissociation enthalpy is different for the different bonds within the same molecule. In such cases, we use mean bond enthalpy. For example, methane. In methane, there are 4 CH bonds which are identical in the bond length and bond energy. But when we break these bonds between C and H in the successive steps, the bond enthalpies are different. So in this case, we take the mean bond enthalpy. Dear students, today I explained you that internal energy and enthalpy are related via equation delta H is equals to delta U plus P delta V. Delta H is the heat exchange at constant pressure and delta U is heat exchange at constant volume. I also explained about the enthalpy changes in phase transformations. The phase transformations, that is the change from the solid to liquid or liquid to gaseous state or vice versa. I also explained that the enthalpy of atomization for the diatomic molecules and polyatomic molecules is different. In the case of the polyatomic molecules, we take the mean bond enthalpy. In the next lecture, we will study about the lattice enthalpy and the way to find out the lattice enthalpy of an ionic solid using Born-Haber cycle. Thank you.